Welcome to lecture 55 on essentials of topology. Continuing with the concept of compactness, in this lecture we will study the well-known Lebesgue number lemma along with the concept of uniform continuous functions. Begin with a result which we will require to prove this lemma. So before stating and proving the lemma, let us prove a result from metric space. What this result says, this result states that if we are having a metric space xt and a subset A of x, then the function f defined from x to set of real numbers such that fx is equal to dxa is continuous, and this notion we have already studied in the previous lecture, that is, this is the distance of point x from this fixed set A. In order to prove the continuity of this function, let us use the notion of epsilon delta definition. So, what exactly we have to justify here, that is, for given epsilon greater than 0, and let us take any x in x, there exists some delta greater than 0 such that whenever this d of xy is less than delta, this difference of, or the absolute value of this difference, fx minus fy, is less than epsilon, where y is an element of y. It is to be noted that whenever we are talking about fx and fy, this function is defined in this way, that is, f of x, this is nothing but distance of x from the set A. And what about f of y? This is the distance of this point y from the set A. Now, as we have to justify that this is less than some real number epsilon, which is greater than 0, so what we can do, that let us begin with this number, that is dxa. Note that this will always be less than or equal to dxa for all a in A, and this is because this is infimum of such real numbers. So by triangle inequality, we can write that this dxa is less than or equal to dxy plus dya, or what we can write, this is dxa is less than or equal to, or this dxa minus dxy, this is less than or equal to dya. Note that this inequality is true for all A in A. So what we can do, that let us take infimum over A on right hand side, and this is possible because this number is less than or equal to d of or dya, and this is true for all A in A. Therefore, what we can conclude from here, that is dxa minus this dxy, this is less than or equal to dya, or we can say that this dxa minus dya, this is less than or equal to dxy. Now interchange the role of x and y. We can also write that this dya minus this dxa is less than or equal to dxy, and here will be dxy itself because d is symmetric. Now combining these two, what we can conclude, we can say that this dxa minus dya, if we are taking the absolute value of this difference, then this will always be less than or equal to dxy. Now let us assume that this dxy is less than delta. Also take epsilon is equal to delta. So what we can conclude from here, that is the absolute value of this difference, that is dxa minus dya, this is less than epsilon, or what we can say that f of x minus this f of y. This is less than epsilon. That's the proof of this result. Moving ahead, and let us see the main result, that is the Lebesgue number lemma. The lemma is stated as, if we are having a metric space that is compact 2, and let us take C as an open cover of X, then this lemma says that there exists a lambda greater than 0 such that for all x in X there is an element in this open cover satisfying this Bx lambda which is contained in G. It means that for every x in X we can find a member in open cover, that is there exists some open subset of X containing this open ball centered at X and radius lambda. Exactly what does it mean? Let us take this set as X. Now if we are taking its cover, even if we are beginning with an open cover, that will have some finite subcover because the space is compact. So let us take some cover of this set X. So this line, this is covering this X. So we are taking different open sets inside this X because all are subsets of X. And now what this lemma states that if we are taking an element inside it, so we can construct an open ball, and that open ball may look like in this way, and that is possible because this is a metric space. But our interest is that corresponding to this lambda which will exist here, we can construct an open ball, and that open ball should be precisely in one of the member of open cover, that is inside it. Now let us see the proof. Begin with, let us take this collection C. This is an open cover of X. Question is whether X is a member of this C. For example, if X is a member of this open cover, what will happen? If X is a member of C, then what will happen? For this lambda greater than 0 and for all X belongs to X, it is to be noted that this ball will always be contained in X, and therefore this lemma can be proved trivially. So what we are going to take? We are taking this open cover C such that X is not a member of it. Further, if this is an open cover of X, what we can do that there exists some finite subcover. So what we can say that there exists some G1, G2 and Gn in C such that this X is equal to union of these G1, G2 as well as Gn. Now let us take the complement of these Gi's. So what we are doing that we are constructing new sets. Let us take Fi, which is complement of these Gi's. It is to be noted that this I lie between 1 to n. What about these Fi's? They will be non-empty first thing because none of the Gi is equal to X, and second thing they will be close to. Moving ahead, and let us prepare a platform for using the extreme value theorem which we are going to use for proving this lemma. So let us define a function. So we are defining a function f from this X to set of real numbers R, and this function is defined as for all x in X, this f of X is defined as 1 upon n summation I is equal to 1 to n this d, ex and fi. So what this function is, this is nothing but this function is actually the average of distances from this ex to fi. This is a well-defined function. Let us see the nature of this function. So what function we have taken here, that is a function from x to set of real numbers, and we have defined this function like 1 upon n, this summation I is equal to 1 to n dx fi. It is to be noted that from the previous result, that if we are defining a function which is sending each x to dx f, where f is a fixed subset of x, then this function is continuous. Now, what this fx is? This is a finite sum of these continuous functions multiplied by some real number. Therefore, this f is also continuous. So, we have we have shown that this function is continuous. Further, it is to be noted that what x is, this is compact. And now, if this x is compact, use the extreme value theorem. So therefore, by the well-known extreme value theorem, what we can conclude? We can conclude that this f takes on a minimum value, and let us take that minimum value be this lambda. It is to be noted that when we are saying that this f takes on a minimum value lambda, meaning is that this lambda is less than or equal to fx for all x in x. Even this lambda will be something like f of x naught, where x naught belongs to x. Now, what we require? We have prepared a foundation for proving this Lebesgue number lemma. Now, we have to show that this lambda is greater than 0 because we have shown the existence of lambda. So, let us try to show that lambda is greater than 0 and this open ball is contained in some g. So, what precisely we have to justify? We have to justify two things, that this lambda will always be greater than 0, and second thing, we have to justify that this bx lambda will be, or this will be included in some g, where g is coming from this open cover. So first we are going to justify that lambda is greater than 0. In order to show that this lambda is greater than 0, what we will justify that this fx will always be strictly greater than 0 for all x belongs to x. And if we can justify that this fx is greater than 0 for all x in x, from here we can conclude that lambda will always be greater than 0. Now, in order to show that this fx is always greater than 0, just let us take any arbitrary x in x. Note that if x is in x, what x is? X is nothing but the union of these gi's I lie between 1 to n. So what will happen? X will belongs to some gk, and what this k is? K is, or we can write that this is for some k, and this k is a member of this set 1 to n. Note that this is a metric space, so it can induce metric topology, and by using that one or even from metric spaces, what we can conclude that there exists some epsilon greater than 0 such that this open ball centered at x and radius epsilon will be a subset of gk. And if this is a subset of gk, what we can conclude from here, that if we are trying to find out distance of x from fk, this will always be greater than epsilon. Question is how we can do it? Because what we are assuming that if this is greater than or equal to epsilon, meaning is that this dxy is greater than or equal to epsilon for all y in fk. Now, if for some y, if for example this dxy is less than epsilon for some y in fk, what will happen? Note that if dxy is less than epsilon, this y will be a member of this open ball centered at x and radius epsilon. And what this is? This is a subset of gk. So from here what we can say that, or what we are showing, that y is a member of fk and y is a member of gk. But it is to be noted that what fk is a complement of gk, so this is not possible. And therefore this dxfk, that is the distance of x from fk, will always be greater than epsilon. Now let us see the nature of our function. The function what we have defined, that is defined as summation of, that is summation I is equal to 1 to n dx fi 1 upon n. Note that this can be written as something like 1 upon n this dx f1 plus so on, plus this we can write dx fi plus so on, continue with it, we can write this is dxfn. It is to be noted that what this distance is, this is always positive, this is always positive, and note that this distance what we have written here, this is always greater than or equal to epsilon. So from here what we can conclude that this fx is always greater than or equal to epsilon upon n. It is to be noted that this epsilon is greater than 0. Therefore, what we can conclude that this fx is always greater than 0. And if fx is greater than 0, we can conclude that this lambda is always greater than 0. So, we have proved this first part. Now, let us try to justify that the open ball centered at x and radius lambda is included in some of the member of this open cover. Actually, what we will show that we can justify that this open ball centered at x with radius, and this is for every x in x. This can be included in some gm for some m in this set, that is 1 to up to n. Question is how is it possible? Let us take this dxfm. Let us take this as a maximum of these dxfi's where I lying between 1 to n, and we can talk about this one because they are finite in the number. Then what we can do, let us see this fx, which is always greater than or equal to lambda, and this is nothing but 1 upon n summation I is equal to 1 to n dx, this is fi. This will be less than or equal to 1 upon n summation I is equal to 1 to n dx, this is fm. And if we are finding the sum, this is precisely this dxf. That is, we have found two bound for this fx, that is fx is greater than or equal to lambda, and this is less than or equal to, this is dxfm. From here now we can claim that what we have written here, that is this Vx lambda will always be included in Gm, because if possible there exists some y in this open ball centered at x and radius such that y is not member of Gm. So what will happen? Note that Fm is a complement of Gm, so y will belongs to Fm. And if y belongs to Fm, from here what we can conclude? We can conclude that this dxy is greater than or equal to lambda. But at the same time, it is to be noted that what y is a member of this open ball, that is this bx lambda, and if this is the member of this open ball, what we can conclude that this dxy is less than lambda. So just see this as well as this one, we reach to a contradiction, and hence what we conclude that this bx lambda is a subset of Gm. And what this Gm is? Gm is a member of this open cover. That's the proof of this well-known Lebesgue number lemma. It is to be noted here that this lambda has also a special name. Actually, this lambda, this is called the Lebesgue number of this open cover what we have taken here of open cover C. Now let us use the concept of this Lebesgue number lemma to discuss the uniform continuity in metric spaces. What we can justify that if metric spaces are compact, the continuous function turns out to be an uniform continuous function. But before coming to that concept, let us recall the concept of uniform continuity, that is a function f from a metric space xt to another metric space yd dash. We say that this function is uniformly continuous if for a given epsilon greater than 0, there exists a delta greater than 0 such that if we are taking any pair of points in x, whenever dx1 x2 is less than delta, it implies that d dash f of x1 and f of x2 is less than epsilon. Having this idea in mind, let us prove a simple result, and which is the relationship between continuous function, which states that if we have two metric spaces xt and yd dash, and these two metric spaces are compact, then the continuous function f from x to y is uniformly continuous. In order to prove this result, let us take or let us begin with this function f from x to y. Note that this function is continuous. Now, if this function is continuous, also it is to be noted that x and y both are compact, and being metric spaces, we can talk about the metric topology. So let us take an open cover of this y. So what we are taking? We are taking open ball centered at y and radius this epsilon by 2. Here epsilon is greater than 0. Y belongs to y. Note that this is an open cover of y. If this is an open cover of y, let us take the inverse image of it, that is f inverse this b y epsilon by 2. What y is? That is y is in y. Let us take this collection as C. Note that this f inverse of these open balls will be open subset of x because the function is continuous, so they will be open subset of x, and what we can say that this is an open cover of x. If this is an open cover of x, let us take the Lebesgue number, that is this is lambda of this open cover. So if we are taking this Lebesgue number as lambda, now corresponding to this epsilon greater than 0, what we can say that there exists a delta, and this delta is nothing but this Lebesgue number. Let us take this delta is equal to lambda. Now we are taking any two elements x1 and x2 in X such that d x1 x2 is less than delta. Then what will happen? This x1 x2, this 2 point set will be member of an element of this open cover by using the Lebesgue number lemma. So this will be a subset of F inverse of B, that is open ball centered at y and radius epsilon by 2, or we can say that F of, that is image of this 2 point set, will be a subset of this open ball centered at y and radius epsilon by 2, or we can say that this 2 point set, that is fx1 fx2, is a subset of this open ball centered at y and radius epsilon by 2, or what we can conclude that this d dash f of x1 and fx2, this is less than epsilon. So whenever dx1 x2 is less than delta, this d dash fx1 fx2 is less than epsilon, and what exactly we have taken that for any arbitrary epsilon greater than 0, this delta is nothing but the Lebesgue number of the open cover which we have constructed here. Therefore, the continuous function f is uniformly continuous. These are the references. That's all from this lecture. Thank you.